So in our next section, we'll take a look at hypothesis tests for population standard deviation. The checking to make sure you're allowed to do them really just boils down to making sure your population is normally distributed, which it will be. Then the types of tests that we can run are the same, left, right, and two-tailed. We've got a formula that will be determining our test statistic. So it's just our chi-squared naught is how you would say that. But the test statistic will be sample size minus 1 times standard deviation squared, otherwise known as variance, divided by our sigma naught, which will come from the previous believed value, that squared for our test statistic. We'll be using the classical approach, so we'll compare that value to the critical value, and the critical value will come from the chi-squared table, just like in the last section, the critical value came from the t-distribution table. And then in comparing those two values, we'll make our decision and state our conclusion. All right, so we have a can of 7-Up states that the contents of the can are 355 milliliters. A quality control engineer is worried that the filling machine is miscalibrated. In other words, she wants to make sure the machine is not overfilling the cans. She randomly selects 9 cans of 7-Up and measures the contents. There's the data. We currently assume the population standard deviation is 3.2. Test the claim that the population standard deviation is greater than 3.2 at a level of significance of 0.05. All right. So what we need is a sample standard deviation. So remember, if you are ever given a set of raw data, don't forget that you can go to Stat and Edit on your calculator to enter that data there. Right? Make sure you get to that L1 list again by going to Stat and clicking Enter on Edit. You can enter all your data into L1. Then you can go to Stat and Calculate and 1var stats and hit Enter to get the necessary information. Specifically, you're going to want, in this case, the sample standard deviation. You want this S, not the sigma. So you want the sample standard deviation, and we'll take that to 3 places, 3.464. That'll be our value for S. So from there, let's look at our hypotheses. We're looking at hypotheses about the standard deviation, so sigma. Currently believed to be 3.2. We're wanting to make sure that it is not greater than 3.2. Okay, so there's our hypotheses. For our test statistic, we've got our chi-squared naught test value, and that was the n minus 1 times s squared over the chi-squared, or the sigma naught squared. So our sample size, well, there was 9 of them, so that's 9 minus 1, that'll be 8, times the s squared of our standard deviation, 3.464 squared, over the currently believed sigma naught of 3.2 squared. And that's coming out to 9.374. So again, that's our chi-squared naught value, or what we would call our test statistic. So for the critical value, what we need to understand is we've got a greater than. So remember, our chi-squared value distribution, our chi-squared distribution looks more of a right skewed. So we're looking at a right tail here. And we will pull out the chi-squared chart. And recall that when you're looking at these numbers, you're always being told area to the right. So, oops, not here. So we're going to be given area to the right. So these first numbers are for those left boundaries where there's a great deal to its right and only a small amount to its left. So we actually want to look in this set of columns over here with the small values of alpha. Specifically, we know that this area is 0.05 from our level of significance. And then like we said before, our n is 9, so degrees of freedom will be 8. So we're looking up 0.05 for the area and 8 for the degrees of freedom, bringing that over, getting 15.507. So this value, just strictly from our chart, 15.507. Okay, so that's our critical value, otherwise known as the chi-squared of alpha. And so just remember the little bit of difference in that this is not centered at 0, right? The 0 is actually here. These are only positive values on the chi-square distribution. So 0 is here, positive values going to the right. Just don't forget that. But with that information, if we go to make our decision, and I think about this picture, well, if my boundary, right, if my critical value for that critical region is at 15.507, but my test statistic is at 9.37, that's not as big as 15. 9.37 is somewhere over here. We don't know where. We don't necessarily know if it's left or right of the peak, and I don't need you to worry about that. Just know its relationship to this boundary to say that that picture would tell us we're going to not reject the null. Right? It's not in the rejection region. And so for our conclusion, we can say at a level of significance of 0.05, if we're not rejecting, we say there is not sufficient evidence to support the claim. And then we look at what we were claiming, what the researcher was claiming, and that was that the population standard deviation of fills on 7-Up cans is greater than 3.2 milliliters.